All right, so what we're going to be looking at here is we're adding to our definitions and our theorems here on about triangle properties that eventually will help us with in-class examples looking for solving for x or maybe solving for a particular angle. But we have to understand these definitions so we know what we're referring to in class. Now, because there's so many of these, I decided to write it out ahead of time. So if you need to, hit pause, write down the definitions first. Please make sure, if nothing else, fast forward, write down what I write down. Make sure you get these definitions written down, and then we'll use it to help us in with the in-class examples. So the first definition I see is a polygon, okay? A polygon is just a closed figure, some closed figure in a plane, in which it's formed by segments, and those segments make the sides, okay? Now, the different parts here we're going to recognize here in a little bit. We'll talk about the sides and the vertex, but something simple that we can think about is even just like a square, okay? So notice we have an enclosed figure in which different segments form the sides of this polygon. So these two segments, here's another segment that forms the side, and then this top segment forms another side, okay? Those guys would be the sides. Then the corners, we can think of it as like points, okay? The corners here, that each one of those would be a vertex, so these would be the vertices of the polygon. We can think of it kind of like the corners where the two segments meet, okay? So those guys would each represent a vertex, and that's what this says over here, okay? The sides, they're the segments that connect the consecutive vertices of the polygon, and then the vertex, that's the point where the two sides of the polygon intersect, okay? So we have our segments forming the sides, then each one of these corners here, each one of those points, they represent a vertex of the polygon. So we could think of this as like vertex A, vertex B, vertex C, and vertex D, okay? Or we could also have something a little bit more complicated. Maybe we have a figure that looks something like this. Don't make fun of my drawing, okay? Maybe we have something like this, in which case we can still call this A, B, C, D, E, and then this last one here where these two segments meet, F. Okay. Now, the thing about a polygon, though, when we name a polygon, we include each of the vertices in the name. Okay. So this would be the polygon A, B, C, D, E, F. Okay. We use each one to name this polygon. Well, you might say, well, Mr. Pinkstros, when we named a plane, we only needed 3 points. Yes, that was a plane that was designated an infamous surface, okay? So we're talking about a surface that stretches on forever and ever. This is not a surface. This is a figure. This is a polygon. So we use each one of these to define the vertices, okay? So this is the polygon A, B, C, D, E, F, okay? Now, a particular polygon that we're going to be focusing on here is a triangle. A triangle is a polygon with 3 sides. Well, you guys know what a triangle is. We have something like this. Oh, that was a terrible side. Let's try that again. A little bit better. Then we have, let's say, A, B, C as our vertices, okay? Now, when we name a triangle, oftentimes they use that delta symbol for a triangle, and then we use the vertices just like we did above to name our polygon, okay? So we would call this the triangle A, B, C, okay? So this is what a triangle is a polygon with 3 sides. Notice we have the sides AB, the side BC, and the side AC, okay? Now, another definition we run into is an acute triangle. Now, an acute triangle, it's a triangle, but every single angle in that triangle is acute. In other words, it's smaller than 90 degrees, but still greater than 0, okay? So if we have an acute triangle, we'd have something maybe like we have this guy here. And maybe we call this LMN. Then angle, going over here, angled, or let's go ahead and call it the measure. So let's call it the measure of angle L would be less than 90. The measure of angle M would be less than 90. And then the measure of angle N would be less than 90. Okay, so all of the angles would be acute because they'd be less than 90 degrees, but then they would also be greater than 0. Okay, so that's an acute triangle. Now, what about a right triangle? Well, a right triangle has at least, in this case we're talking about, we can't say the word at least, it has one right angle, okay? We can't have more than one right angle, but it has one right angle, okay? So in the acute triangle, every single angle was acute. But with a right triangle, one of the angles is a right angle, okay? So one of the angles has to be 90 degrees. So with a right triangle, we just need this one angle to be right or to be 90 degrees, and then we'd have a right triangle. So we could call this E, we could call this D, and we could call this F, okay? So the triangle DEF here, that would be a right triangle. Now, earlier we kind of talked about this. I'm going to kind of add this here. We've mentioned this a little bit in class before about the legs and the hypotenuse, but maybe now we can add a little bit more to it, okay? So the legs of a right triangle, okay, those are the sides of a right triangle that form the right angle. Let's see, where am I at? That form the right angle. Okay, so in our picture here, this guy would be a leg, and this guy would be a leg. Okay, so DE, the segment DE and the segment EF, those guys would be legs of this right triangle. Now the hypotenuse, that's the side of a right triangle that is opposite the right angle. Okay, so the hypotenuse, that would be DF here. Okay, so this guy right there, let's try that again. This guy right here, this would be our hypotenuse. Okay, it's the side opposite the right angle. Okay, now that kind of helps us with the HL postulate that we talked about earlier that said if the hypotenuse of two right triangles is the same, and the leg of two right triangles is the same, then we could claim that those two triangles were congruent by the HL postulate. Okay, now the next definition we're looking at here is the obtuse triangle, and that's a triangle, you guessed it, within obtuse angle. Okay, so the obtuse triangle, maybe we have something like, this guy here. Notice that large angle there, that's an obtuse angle. So we have one obtuse angle here, and we could call this, let's say, maybe I, G, H. Okay, this would be an obtuse triangle, okay, where the measure in this case, because G is the large angle here that I wrote, or that I drew, so this would be my obtuse angle, where the measure of angle G is greater than 90. Okay, so remember, an obtuse angle, the measure was greater than 90, but then less than 180. Then the next definition we're looking at here is an equiangular triangle, okay? Now, what does that remind you of? Well, that's the same type of word that's also involved with equals, right? So think equals, okay? In other words, we have the same, and then what does angular mean? Well, the word angle is in there, right? So we're saying same angle. That's essentially what it's saying here, same angle triangle, okay? So an equiangular triangle, that's a triangle with three congruent angles. Every single angle in that triangle has the same measure, okay? For instance, I have this triangle here. Oh, let's try to do that a little bit better. It's a little bit better. That looks a lot closer to have an equiangular triangle. So we have L, J, and K. Okay? What they're saying is each one of these angles have the same measure. Okay? So the measure of angle J is equal to the measure of angle K, which is equal to the measure of angle L. In other words, each one of those angles are congruent, okay? Now, another thing that you need to notice about the equiangular triangle, they will always be acute angles, okay? So this will always be an acute angle, or not acute angle, wow, acute triangle. Okay, so this will always be an acute triangle because all the angles will be acute. Okay, so since all the angles are acute, this would be an acute triangle. Now, the next one we're looking at is a scalene triangle, and that's a triangle with no congruent sides. Well, all that means is every single side, each of those segments that form the side of the triangle have a different measure, okay? So each side has a different measure. So a scalene triangle, maybe we would have something like this. Maybe extended that out a little bit more. There we go. So all that's saying there is that this side, and this side all have different measures. In other words, they don't have the same length. So this measures some length, this measures a different length, and this measures a different length. Okay, so that's a scalene triangle. It's a triangle with no congruent sides. Okay, now an isosceles triangle, that's a triangle with two congruent sides. So the previous one, no sides were congruent. Isosceles has two congruent sides, okay? So when we have an isosceles triangle, maybe we have something like this, where these two sides have the same length, okay? Now, we call the legs, that's the congruent sides, okay? So we would call these guys the legs of the isosceles triangle. Okay, so the congruent sides, the sides that have the same length, those would be the legs of the isosceles triangle. Then the guy that is not congruent, that's what this says here, the guy that is not congruent, this guy would be the base. So this guy is the base of the isosceles triangle. Okay, then the vertex angle is the angle across from, move it over, there we go, the base. Okay, so I was trying to get you to see that. That guy right there, this guy would be our vertex angle. Okay, that guy would be the vertex angle. Now the base angle, this should actually probably say base angles. Okay, the base angles, see if I can move it over. There we go. So if you need to, hit pause and write this down. But the base angles, those are the angles formed partially by the base, okay? So when they're talking about the base angles, well, it's down here with the base, okay? So remember, this line right here, this was our base. These guys right there would be the base angles, okay? So this guy and this guy, these guys form the base angles. Okay, so an isosceles triangle, that's a triangle with two congruent sides. The two congruent sides are the legs. The vertex the vertex angle is the angle across from the base being the side that is not congruent, and the two angles that form the base, those are the base angles, okay, that help form part of the base. Now, the next triangle we're looking at is an equilateral triangle. Now, remember that word equals, and lateral means side, okay? So when it says equilateral, it really means equal sides. So equiangular was equal angles, okay? Angles that have the same measure. This is saying equal sides. So this is a triangle that has all sides that are the same length, okay? So it's saying I have some triangle. Let's try that partially again. Each side would have the same measure, okay? That would be an equilateral triangle where all three sides are congruent. Then, the next thing we're going to be looking at is the triangle sum theorem. So all these other ones were definitions. We're trying to define the different triangles we could come across, okay? So we had, just kind of backtracking here, we had a polygon, then we said a triangle was a three-sided polygon, acute triangle had three acute angles, a right triangle has a right angle, obtuse triangle has an obtuse angle, equiangular triangle, three angles are congruent, scalene triangle, no sides are congruent, isosceles triangle, two sides are congruent. Equilateral triangle, three sides are congruent. Okay, then the triangle sum theorem, this is what we need for some of the examples in class. The triangle sum theorem says the sum of the measures of the angles of a triangle is 180 degrees, okay? Any triangle, does not matter which triangle we're talking about, all three angles will always add to be 180 degrees. So if I have some triangle here, and we could call it, let's say, A, maybe B, and maybe C. There we go. Then the measure of angle A plus the measure of angle B plus the measure of angle C has to add to be 180. Doesn't matter which triangle it is, it always adds to be 180. Then a couple of other theorems we want to add here is T22. The acute angles of a right triangle are complementary. Okay, so if we have a right triangle, let's say this is a right triangle, and maybe we could call this our ABC again. Okay, what it's saying is these angles here, they're acute angles, but the acute angles of the right triangle have to be complementary to the right to our right angle here. Okay, or excuse me, sorry, they're going to be complementary. They add up to be a right angle. I was misspeaking there, but complementary, remember back to what we talked about before, that means they add to be 90 degrees, okay? So what they're saying is the measure of angle B plus the measure of angle C has to add to be 90 degrees. They're complementary. Now, the reason they have to be complementary, this is what I was kind of saying, but I was saying it wrong a second ago, is that since this is a right angle, we know that all the angles add up to be what? 180. That's just what we said there. So if this is 90 degrees, then the other two angles have to add up to be what? 90. That's the only way it works, right? 90 plus 90 is 180. So the measure of angle B plus the measure of angle C has to be 90 degrees in order for all the angles to add up to be 180. So just remember those two acute angles add up to be 90. They're complementary. Okay? Now T23. The measure of each angle of an equiangular triangle is 60, okay? So if I have an equiangular triangle, remember all angles are the same, then each angle has to be 60 degrees, okay? This angle would be 60 degrees, this angle would be 60 degrees, and this angle would be 60 degrees. So if I have an equiangular triangle, each angle is 60 degrees. Well, how do we know that? Well, if every single angle adds up to be 180 and each angle is the same, how many angles are we dealing with? 3, right? Well, if they're all the same, can't I just take 180 divided by 3? Yeah, because each one has the same measure, right? So if I divide that out, I get 60. So when I have an equiangular triangle, each angle has to be 60 degrees because 60 plus 60 plus 60 is 180. Okay? Last theorem here, T24. If a triangle has one right angle, then the other two angles must be acute. Well, this is kind of what I was trying to say earlier in the example above, is that with our two angles here, we know that these two angles here have to add up to be 90 because we have a 90-degree angle here, and 90 plus 90 is 180. That's what they're saying down there. If this is 90 degrees, these have to be acute because two smaller acute angles that add up to be 90 would get us to 180 degrees, okay? So if a triangle has one right angle, then the other two angles must be acute. Why? Because again, all the angles have to add up to be 180. Okay, so they're saying if I have this right triangle here, this is A, this is B, and this is C, then angle B and angle C have to be acute because, again, angle B plus angle C has to add to be 90 so that when we add it to our right angle, we get 180 degrees. Okay?